hit record on this for our purposes here. We're going to have the same setup as Tuesday. We do have one less team, so we might be able to wrap up a little bit earlier than we did on Tuesday. We'll do some housekeeping and then we'll dive into pitches. The one additional note we'd like to make today is questions during the Q&A portion today are open to all participants. So please do join us in asking other teams questions. If you don't feel comfortable, or if you'd prefer us to moderate those questions for you, feel free to send in the chat either to myself, Lindsay, or Katie Smith, or Alex as well. And we can all ask those questions on your behalf, but do feel free to participate in the Q&A, whether you're from the IAP or a competitor team. If you have any questions about Zoom, any technical or technology related questions, you can either message me via Zoom, or if that's not working for you, feel free to email me, lindsay.mcgurk@nrel.gov. Any prize related or technical questions about lithium or lithium extraction, it can go to geolithium extraction@nrel.gov, and that will go to our prize inbox. If you do have any questions throughout today about anything, feel free to drop those in the chat as well. Once again, thank you to our IAP members for joining, participating, and supporting our teams throughout the prize. We do appreciate all of your insight, help, and support that you do provide to the teams. We will be doing same setup as Tuesday, 10-minute pitches, 5-minute Q&As, and we will hear from the remaining 7 semifinalist teams in today's session. So with that, we can get started with our pitches. Select Pure
Lindsay,
Lithium.
can I do a, I'm sorry, can I do a
quick?
Yeah,
please.
Just welcome to everybody. Sorry, I should have mentioned it while we were chatting on the phone earlier, but for those that weren't on the call for day one, hi everybody, I'm Alexandra Priestashef. I am with the Department of Energy Geothermal Technologies Office, and I am also the Geothermal Lithium Extraction Prize Lead. And I wanted to also welcome everyone back to day 2 of our phase 2 semifinalist innovation pitches. We had a great day 1 of presentations on Tuesday, and I'm excited to hear the remaining of the semifinalist pitches today. As Lindsay mentioned before, we had a lot of good feedback and questions from the prize team. So we want to, again, open up the chat, the 5-minute Q&A session to the other teams. And how we're going to do that is all the teams, if you have questions for your fellow competitors, if you could just enter those into the chat box. And then once the IAP has the opportunity to ask questions and provide feedback, we'll go ahead and jump into those. But we want to make sure that 5 minutes is still primarily dedicated to our IAP members today. So, and also thank you again to our IAP members that will be on the line. And yeah, let's go ahead and get started. Thank you, Lindsay. All right. First up, we have Select Pure Lithium from the University of Illinois. And whenever you're ready, please go ahead.
Hello, thank you, organizer. Can you hear me okay?
Yes.
Yes, so my name is Hen Yang. We are team Select Pure Lithium. Next page, please. Next slide, please. So our team is formed between UIUC and Xeron Advanced Batteries. Our team captain is Dr. Paul Brown. He's a professor at UIUC. His group studies functional materials for energy storage and harvesting. Dr. Ben Zahiri is a research assistant professor working together with Paul. From Xeron, we have Dr. John Cook and myself. We have been in the battery industry for over 10 years. So next slide, please. So this is a wordy slide. I'll just go quickly through them. So we propose to use direct plate lithium cobalt oxide as a redox membrane to extract lithium hydroxide. So this concept is unique in that we induce an electrochemical reaction on the membrane itself Hopefully, the concept will become clear in the following slides, and we also prepared a video to help demonstrate that. So in phase 2, we have demonstrated successful electrochemical extraction and release of lithium ion in lithium chloride model solutions. We have also done life cycle cost analysis, and we show that our cost at $5,000 per metric ton is much lower than the market average. We believe with further optimization, the cost could be even lower. In phase 3, we plan to test the direct plate membrane in real geothermal brine sample from the Salton Sea, and we plan to extract lithium hydroxide in HCl continuously. And we plan to study its stability and cycle life and develop process flow and waste treatment. We also plan to evaluate extraction efficiency, energy consumption, and life cycle costs based on experimental data collected in phase 3. Next slide, please. So as we all know, the booming electric vehicle market requires a lot of batteries, which requires a lot of lithium salt to synthesize these batteries. The Salton Sea geothermal region has a large lithium reserve. If we can have an efficient lithium extraction method, this can become a secure and reliable lithium source for the US. We are a group of battery researchers. So when we look at this question, we're wondering, can we use some battery concepts to help address this battery supply chain issue? Because by its nature, the battery material is already engineered to shuttle lithium ion in and out for thousands of cycles. And we believe we have a good idea in this regard. And then on the right-hand side, this figure panel shows a few years ago, Xerion invented this direct plate technology, which is an electroplating technology from a molten salt environment. So we form a lithium cobalt oxide directly from molten salt on a conductive current collector. So this is fundamentally different than conventional battery electrode because conventional electrodes contains organic binder and conductive additives that are porous. In our case, it's monolithic, fully dense, so it can block the solvent molecules and only allow lithium ion to pass through. So we believe this structure aspect really makes it an excellent membrane material. Additionally, we can electroplate lithium cobalt oxide on different porous structure, which makes the fabric, which makes our choice of substrate just more versatile. So next slide, please. So this is a schematic showing the extraction mechanism. In a nutshell, the lithium hydroxide extraction cell is formed of two different electrochemical cells separated by the redox membrane. On the left-hand side, there is hot lithium brine, and when a current runs through the counter electrode and the redox membrane, lithiation happens on the redox membrane, and chlorine gas evolution happens on the counter electrode. In the right-hand side chamber, it started with a dilute lithium hydroxide solution. A reverse current passed through the redox membrane to release lithium. Hydroxide ion formed together with hydrogen evolution reaction, and this process gives us more concentrated lithium hydroxide solution, which we extract after this process. Chlorine gas and hydrogen gas can be collected and form value-added HCl solutions. So we made a video to help demonstrate this concept. Please play and make sure you're unmuted.
The Select Pure Li team proposes a simple and energy-efficient method to extract lithium from geothermal brine and convert it into high-value lithium hydroxide. The two-stage reaction begins with the lithium extraction and intercalation into the direct plate membrane, while at the same time, chlorine gas is evolved on the counter electrode. In the opposite chamber, lithium ion is released from the membrane and combines with hydroxide ions formed from hydrogen evolution reaction, producing high-concentration lithium hydroxide solution. The key component is the direct plate membrane, an electroplated battery material only permeable by lithium ions. The estimated lithium pass-through at the Salton Sea geothermal region exceeds 24,000 metric tons per year. If fully developed, lithium extraction from geothermal brine could provide a secure, long-lasting lithium source for the United States.
Slides, please. So in our previous work, we have demonstrated a high rate discharge of a very thick direct plate LCO material. So here the LCO is 120 micrometers thick, at least double the current state of art in terms of lithium storage capacity. So the red curve is a C/10 discharge, which means a complete lithiation reaction in 10 hours. So this translates to lithium hydroxide extraction at a rate of 60 grams per meter square per hour. As you can see, we can further increase the operation rate to 2C, which means 20-fold higher extraction rate is possible if we don't have to do utilize the full lithium storage capacity of the membrane. So for the panel on the right-hand side, this is our phase 2 progress. We have optimized our electroplating process on carbon paper. We chose carbon paper for its low cost and high chemical stability. We want to stress that these materials are plated from a very corrosive molten salt environment at high temperature. So the composite electrode is corrosion resistant and can withstand high temperature. So the dense LCO layer formed on carbon paper, the zoom-in view shows its layer structure. So this layer structure indicates the diffusion channel are aligned parallel to the lithium extraction direction, which should be optimum for extraction kinetics. Next slide, please. So we further studied the electrochemical behavior of our redox membrane. The cyclic voltammetry diagram shows reversible lithium release and uptake in a 1 molar lithium chloride solution. We further demonstrated lithium release and uptake in constant current mode, which is more relevant to practical applications. With this curve, we can estimate the energy efficiency at 0.9 kilowatt hour per kilogram, which is already below our 3.7 target. We can achieve a high energy efficiency because this is a battery material, and battery material is engineered for high efficient interconnection and de-interconnection of lithium ions. So we believe this is a key differentiator for our technology. At the moment, with this applied current, our extraction rate is 3.2 grams per meter square per hour, which is below our target. But this is because we intentionally slapped a small current to utilize the full range of lithium storage capacity in the membrane. In practice, we can limit our extent of reaction, and as the CV curve shows, we can go at least 10 times higher current for this particular material, and further material improvement can lead to higher extraction rate. Next slide, please. So our project goes at 3 different levels. At the concept level, we have proposed the redox membrane concept for direct extraction of lithium hydroxide from geothermal brine. In phase 2 and 3, we're working hard to demonstrate lithium hydroxide extraction with the goal of reaching energy consumption below 3.7 kilowatt hour per kilogram, with a production rate higher than 60 grams per meter square per hour, and with the life cycle cost below $5,000 per metric ton. And in the longer term, our team aim to scale up lithium hydroxide production domestically using our redox membrane concept. With Xerion's industry experience and UIUC's world-class research resources, we believe we can achieve this goal. Furthermore, Xerion's direct plate technology is already a low-cost material production system. We don't have any emission from the plating bath. So if we can integrate the extracted lithium hydroxide into Xeron's battery production cycle, we can double the impact on cost and environment and on environment. So since we were selected for phase 2, last Christmas I traveled to the Salton Sea region and took this photo. It was a beautiful area, and any technology we are inventing should really keep it this way. So thanks, organizers, for giving us this opportunity.
Thank you very much. Like pure lithium. So now we'll go ahead and open up to our industry advisory panel for some questions and feedback. And teams, if you have any feedback for this team, please go ahead and put those into the chat. And IAP, if you have a question or feedback, just go ahead and unmute yourself.
Is there a temperature limitation at all?
So the material can withstand temperature up to 600 degrees Celsius. I think the temperature will be limited on the brine side. We are wondering if we can, this is we want to do some tests, and we want to see if we can increase the pressure and allow even higher temperatures. That should be beneficial for kinetics and preventing minerals from crashing out of brine potentially.
Thank you.
So we're waiting on some questions from other folks. I'll go ahead and jump in and ask one. Can you talk a little bit about the barrier that your extraction process addresses with the current state of the art of direct lithium extraction?
So I think for a direct electrochemical extraction, the challenges we are addressing is the membrane material, which usually induce high voltage drop across the membrane. Our invention is to use a battery material as that membrane, because the voltage hysteresis during lithium interconnection and de-interconnection is already very low. So if we can achieve this addresses the inner challenge. In addition, the direct plate material is fully dense, and it can be plated in a thick format to block out the solvent, and the material is lithium selective, so it can potentially block out all other cations and anion species. So we believe this could, allow us to do a single-step extraction reaction in the system.
Thank you. Thank you very much. If any IAP have any questions, please feel free to jump in. We did get a question in the chat box for you. What is the lithium to sodium selectivity of your material?
So in our fabrication process, we do have sodium ion in our plating environment, but we don't really have much sodium in the system. So that shows the selectivity of lithium over sodium. So we have tried this, but in the geothermal brine, it's a different chemical environment. We need to do experiments, but fundamentally, we don't think sodium will have a higher selectivity than lithium.
Okay. Thank you. All right, we have about 30 seconds. Is there any other final questions? If not, we'll go ahead and jump to the next presentation. Thank you. All right. Next up is team Pober-Strauss from Boston University. And whenever you're ready, please go ahead.
Hi, can everybody hear me?
Yes.
Okay, great. Hi, we're Dick Pober and Mike Strauss. I'm Mike Strauss. We're sorry we missed the memo about getting a clever acronym for this. Next slide, please. We're two material scientists with over 80 years of experience between us, so we're kind of old guys. Dick has been affiliated with BU, MIT, and Harvard. He's founded and worked with small companies and his patents dating back to the 1970s on relevant technology for this. I've worked mostly in process development and scale-up and renewable energy, mostly in small companies, and I've also been a founder in some companies. Next slide, please. And the basic technology is ceramic lithium ion conducting membrane, a class of materials known as lithicons. They're used in batteries. Lithicon is a lithium super ion conductor. The crystal structure has channels so lithium can flow through. Basically, you put a membrane between a brine and hot water, apply a voltage, lithium selectively flows, you get lithium hydroxide on the output side. The electrochemistry says you also get hydrogen forming on the product side and chlorine gas on the brine side. It's just the electrochemistry, mass and charge balances at work. This stuff works better at high temperatures because it's higher conductivity. Unlike metals, ionic conductors are better at high temperatures. So we can also run it to concentrate the lithium hydroxide. It's a simple system. The product is lithium hydroxide. Inputs are water and electricity, no other chemicals. Next slide, please. The cost drivers are basically three things: electricity, membrane, and electrodes. The electricity use is basically 1 kilowatt hour per kilogram of lithium hydroxide produced per driving volt. We're going to assume that we run this at 5 volts. So that's basically $1 per kilogram of lithium hydroxide, and that's 20 cents a kilowatt hour, which is standard for California. But we figure this should actually be less because we're doing this at a power plant. So we should be getting behind the meter pricing without the transmission and distribution. So more likely around 60 cents per kilowatt, 60 cents per kilogram of lithium hydroxide. This compares well with the current price of lithium hydroxide, which goes between 60 and 70 bucks a kilogram, FOB China. Higher voltages are used because less membrane materials is needed. And I'll show this fundamental trade-off later. The membrane itself has its own trade-offs. Thinner is better, less resistance. But you want enough thickness so that you've got mechanical robustness. So that's another fundamental trade-off. Higher conductivity is better, and so you want high temperature. High temperature is good. If you said you want to do this at 800, we would say fantastic, but we're doing it at 100. The electrode material needs to be inexpensive and inert to the hot brine. And we see this whole thing fitting in between the energy extraction and the brine re-injection. Next slide, please. So in phase 1, there it is, yes. In phase 1, we said we would select and test materials for membranes and electrodes in phase 2. And in phase 3, we said we would model continuous systems, both co and counter current, and design, build, and test prototype system at about 1 liter per minute. Next slide, please. What we promised, we would make and test materials, and we've done that. And we've also moved ahead and done some of the modeling for continuous systems. So we're working on phase 3 right now. Next slide, please. What we've done in detail. We reviewed the literature and we rejected sulfur-based materials because they don't do well in water, even though they have very high conductivities. We made some compositions and we also bought some from commercial processors. The processing is standard ceramic processing. We're talking about grinding, milling, calcining, forming, sintering. It's basically the same processing you would do to make a toilet bowl. This is our test rig. The black rod on top and the black plate on bottom are electrodes. They sandwich a lithicon membrane, brine goes in the bottom, and water in the plexiglass tube. We just got some results back. We didn't have time to put them in this pack, but we started with a brine with 200 ppm lithium and over 50,000 ppm sodium. We put distilled water on top, applied a voltage, recorded a flowing current, and then we analyzed the distilled water for lithium and sodium. The lithium to sodium ratio flipped by over a factor of 3,000. So this is highly selective for lithium. We will continue testing with other components. Next slide, please. Electrode testing. Well, we started with Monel because we thought that should be pretty good, but it turns out it started corroding in the brine. So we went to graphite. It's inexpensive, it's stable, so we're going with it. We found the electrodes don't need to be in contact with the membrane. So that opens up more open membrane space and less membrane needed. Next slide. So now let's go into continuous flow modeling. Consider 2 chambers separated by a membrane. What we want to do is set the flow rates between the brine and the product water. If you change, you can change the counter current by changing the direction, basically a minus sign. You set the input concentrations. You can calculate the chemical potential difference across it. You said how much lithium you want to extract. We said we want to go to 90%. And then the big question is, how much membrane do you need to do this? That's what the simulation goes for. Next slide, please. So here are some results. The graph on the left shows the membrane needed for a 6,000 gallon per minute brine system. The blue lines are for co-current flow, the orange lines for counter current flow. At 1 volt, you need about 170 square meters. Going to 5 volts reduces the area to about 50 square meters. So we think that's why we chose the 5 volts. Going to the right graph, we ask what happens as you try to concentrate the product. Basically, what you're doing here is you lower the flow in the product channel. So at 200, a factor of 200 in concentration means instead of flowing 6,000 gallons per minute, you're flowing 30 gallons per minute of hot water. And we see only a modest increase in membrane area needed. And this is because the electrochemical activities across the membrane has a relatively small effect. It is not the driver in the system. It is pushing the stuff through the membrane. We also see that by running countercurrent, as we expected, we would get an improvement, in this case around 6%, and it's a very easy implementation. You just swap piping around. So what does all this mean for costs? Well, 100 square meters of membrane at about a millimeter thickness translates to about 300 to 400 kilograms of active material. We're talking about standard processing, standard ceramic powders. So let's call it $100 a kilogram. That would be a pretty pricey toilet bowl. That comes to around $50,000 for the active material for a 6,000 gallon per minute system. Let's compare this to the revenue that gets generated. 6,000 gallons per minute at 200 ppm of lithium produces 18 kilograms per minute of lithium hydroxide. Current price is 60 to $70 a kilogram. So this system is producing over $1,000 a minute of revenue. That means the active material part has a payback period of time of roughly 1 hour. This all says that extracting lithium is a license to print money at $1,000 a minute. Some plant manager is going to be very happy. Next slide, please. We want to thank our IAP advisor, Katrina Gerber. She's been really helpful. She got us details of brine compositions, and she talked us off the ledge of doing this at 300C. We wanted to do that because the kinetics are better. She kindly explained to us that there are lots of problems with dissolved silica and really practical problems with scaling, and you really don't want to do it at the input end. So thank you, Katrina. Next slide, please. What do we need? Well, we'd really like some real brine. That would be helpful. We'd like to know details of handling. Like, what does a real plant look like? What sort of piping do they use for this stuff? How do we connect it to the system? How much space is available for storage? If we're going to pump out 30 gallons per minute, you need a tank. You're not going to just use 50-gallon drums. And importantly, what is the purity that the market wants? We don't want to spend a lot of time trying to get a system that produces 6 nines when battery buyers buy at, say, 98% and do their own finish processing. So we really need to know a little more about the market, how it's handled, how a real system works. Next slide, please. So thank you very much for your attention, and I'll be happy to try to answer any questions.
All right, thank you very much. That was a great presentation. We'll go ahead and open it up to IAP members for any questions or feedback that you might have. And teams, please go ahead and put some feedback or questions in the chat box.
Mike, it's Andy Robinson. Andy Robinson, can I ask a question?
Sure.
Yeah. What's the effect of the starting composition on the brine side, if you like? If it's a more concentrated lithium chloride solution, how does the system perform? Does concentration have a big effect or a minimal effect?
We haven't tested that, and certainly we would want to test with appropriate brine compositions. But generally, you would think that increasing the concentration of lithium is just going to help it, bang against the membrane and get through. You're helping it with a voltage, but you would think higher concentration helps you.
And then on the hydroxide side, are you getting to similar hydroxide as you would in, say, a modified chloralkali cell, where you're producing hydroxide solution on the other side? You kind of limited to that same lithium hydroxide concentration in the solution?
I'll be honest, I am not familiar with that. I'd like to learn more. If that's a limitation on the system, if there's some electrochemistry that we're not taking into account, we should be doing that. So yeah, any information you have on that would be really helpful.
Right on. Okay.
Let me make a note of that.
I've got a final question. Sorry for hogging all the questions.
Sure.
I'm assuming like suspended solids or any sort of particulates would be an issue. You would need a kind of pristine solution with no suspended solids, I assume. What are your sort of thoughts on that?
I think that, you know, certainly in general, that would be nicer. But remember, we're doing the extraction of the lithium is perpendicular to the flow of the system. So we're not flowing the fluid into the membrane and asking it to please push through. We're saying go parallel to the membrane. So I think while you don't want particulates, you'd expect it to be at least somewhat robust to small amounts of it in there.
Great, thanks. Interesting material. Yeah.
Thank you.
Yeah.
We have one question in the chat box for you. Are there limitations in terms of scaling up membrane fabrication and area considering high pressure temperature requirements?
I don't foresee any. You know, again, this is standard ceramic processing of this sort of material. And I think of tape casting, tube casting, where if you go to the capacitor industry, you know, they've got these giant tape casters, I don't know how many feet wide, just spewing out, you know, long, thin films and piling them on top of one another. So fundamentally, I don't see a processing problem. The issues you bring up of, will this withstand high pressure temperature? I think that remains to be seen in more detailed testing. Sorry.
Thank you. Are there any other questions from our IAP members?
I got one more question. Sorry. No, so I'm intrigued. So the material, do you need to sinter it first to form a stable ceramic phase, and then you form it into a membrane, or can you do it all in one step process?
You know, I'm talking typical ceramic processing. You take a bunch of powders, you grind them together. What you're trying to do is getting intimate contact, and then usually there's a calcining stage. That's where you heat it up to try to get, you know, some diffusion through the minute powder, and then you do a second grind, and then you maybe use tape casting or some sort of extrusion if you want to make a tube. So you're kind of asking, well, can you do that first grinding and do sort of calcining and sintering in one step? Is really what you're asking, I think. And I think the answer is maybe. I don't know if Dick's on the line. He's more of the expert on that part. Maybe, Dick, you have some words of wisdom. But I don't think that that's a major cost driver in making this stuff.
Sure, yeah.
Yeah, in a couple of words, if I'm on.
Yeah, you're on, Dick.
Yeah, okay. So if you look at the substrate business for either hybrid electronics or application substrates for putting on these electronic components, or silicon on sapphire, stuff, but polycrystalline ceramic materials. And to address the original question, yes, the way to make it and the way these were made was to cast the membrane as from a suspension and then fire that. And most of these, depending on what you want to make, if you go to tape casting, that membrane comes out as a flexible item, and it can go directly into a furnace if you want. In most cases, it's shaped to a planar structure and then fired. And of course, they're hard as up when they're done, so you know there's no issue. But on a dollars per square meter, it's one of the cheapest way to make ceramic materials.
Thanks.
All right. Thanks so much for that. We're at time, so we'll go ahead and move on to our next presentation. All right, ELLEXCO from George Washington University. Whenever you're ready, please go ahead.
Yep, I'm ready. Yeah, hello, everyone. I'm Ling Chun Kong from the George Washington University and from the group ELLEXCO. And the ELLEXCO stand for the Electrochemical Lithium Extraction. And our IAP member is Kevin Brown. Next slide, please. And our team consists of my advisor, Dr. Shitong Liu from the George Washington University, and myself. And our lab is equipped with the instrument needed to performing the lithium extraction test, including the ICP-OES for the element concentration measurement, and also the potential set for performing the electrochemical test. Next slide, please. And our proposed technology consists of 3 steps, which contains the electrochemical silica removal and a selective lithium extraction, and then the electro-driven generation of lithium hydroxide. And during phase 1, phase 2, we already built up a continuous flow device for lithium extraction, and we are successfully fabricated the lithium selective electrode and characterize their electrochemical performance. And then we also talk with our IAP member and try to optimize the design. And for the next phase, we will test the performance in a real geothermal brine, and we will also consider to integrate all the 3 steps together and evaluate the overall direct lithium extraction performance. And then we'll also consider the high silica concentration in the next step. Next slide, please. This is just a same description about how the electrochemical process work. We propose the integrated electrochemical process, which has totally 3 steps, because we know that geothermal brine contains a very high silica concentration. So we propose to remove silica first from the brine with electrochemical way. And then the silica-free geothermal brine will go through another electrochemical process, which is the selective lithium extraction with a lithium selective electrode. And then next step is we utilize another electrochemical process to generate lithium hydroxide from lithium chloride. Next slide, please. And the advantages for the electrochemical process is only electricity will be the input to remove the silica, extract the lithium, and then produce lithium hydroxide as the final process. And the total process is a closed loop process, and we only use pure water input, which is also a circulated pure water. We're not consuming any pure water, and there's no waste to consume. Next slide, please. So firstly, we know that the Salton Sea geothermal brine has around 340 milligram per liter of silica, and the geothermal brine pH is around 5.5 to 6, and the temperature is around 100 Celsius. And we all know that after flushing, the silica concentration will increase, and after the geothermal brine is cooled, the silica solubility decrease very much and lead to the formation of silica scale. And because other ions also present, such as iron, aluminum, such metal silicate will perform as precipitate. And it will become an issue for following lithium extraction. So we propose to remove the silica at the first. And next slide, please. Yeah, so electrocoagulation for silica removal, this is what we propose to use in the first step. We showed a previous study that reported silica removal used electrocoagulation in a geothermal brine. And when the voltage is applied, the iron sacrificial electrode dissolved and is generating iron hydroxide. And in this process, silica will be removed by precipitating as iron silicate. And we can see that at different temperature, silica concentration decreased along a very short time, within tens of minutes. And this study gave our evidence and confidence to use the electrocoagulation to remove the silica at the first step, because we also know there's already iron or some other metals in the Southern Sea geothermal brine. And after we apply a voltage, they can form metal hydroxide. And then silica will be precipitated as metal silicate. Next slide, please. And after that, we already fabricated electrode using lithium intercalation material to have a lithium selective electrode. And we run the CV for a pure lithium and a lithium together with magnesium and calcium with a very high concentration. So we can see that from the CV curve, there's still only one redox peak for lithium, which is lithium captured from the brine and from the solution and released back to the solution. Next slide, please. And this is the demonstration about how we capture the lithium from the brine. So we have a continuous setup, and in this capture process, the brine will feed into the cell, and the pure water will the pure water channel will be closed. And then we apply a voltage, and the brine will flow into the cell, and we apply a voltage, and the lithium will intercalate it into the lithium intercalation material. And the right figure shows that we only use the milligram scale of active electrode material, and we can achieve a lithium selective extraction within tens of minutes. And next slide, please. And after we get a lithium extracted into the electrode, and in the release process, we switch the feed from the brine to pure water and get reverse the voltage and get the lithium released back to the water and get the concentrated lithium chloride. And then we feed the lithium chloride into another electrochemical process and obtain lithium hydroxide just by electricity input. And next slide, please. The value and the advantage of our technology and our total design is we have a rapid lithium extraction than the traditional lithium extraction method. And we have a high lithium extraction selectivity using a lithium selective electrode. And we minimize the chemical input. Almost there's no chemical, just the water input. And we have a high purity of lithium hydroxide as a product. And also we have a electricity driven integrated setup to have a total lithium extraction. Next slide, please. And the support we may need from the organizer, or for the next phase, we may need some real brine from Salton Sea, and also we may need some information about what we need for integrating our technology to the existing geothermal brine plant facilities, and also what we need to scale up the test and validating the prototype device. Next slide, please. And then finally, so from the survey we got, lithium hydroxide is more demanding in the future lithium market. And we propose to have a relatively low cost and a relatively high purity of lithium hydroxide, which is have a good fit for the fast and growth lithium market. Next slide, please. And finally, the project goal is we use several hours to have lithium extraction performance and have a higher 80% higher lithium hydroxide purity. And for the sustainability, we decreased the water consumption, also the chemical input. And finally, for the economics, which is competitive to market lithium hydroxide, we calculated from what we have in the literatures before. It is comparable as the intercalation material has a competitive price as the for the final product. And next slide, I think that's the end of the presentation. Thank you for listening.
Thank you very much. So now we'll go ahead and open it up to our IAP members for some questions and feedback. So we're waiting for our IAP with their questions and feedback or questions from the audience. I'll go ahead and ask one. Can you describe the barrier that your technology addresses with the current state of direct lithium extraction?
So I think that the compare with the current technology, so what we propose is an integrated electrochemical process. So we only use 3 steps just to use electricity as input to pre-treat the brine, extract the lithium, and produce the final product as together. Just with only electro-driven process, it will become more. I think it's more feasible for us to have a possibility to input to put it in a real industry.
I can also chime in here. So I'm supposed to give the presentation, but I had the power outage 1 hour ago, so my student just have 1 hour time to prepare for this. Anyway, so our technology comparing to the current existing technologies. So comparing with ion exchange and solvent extraction, so our technology does not require the use of chemicals. It's totally driven by electricity. And also, we don't require the brine to pass through a barrier so that we don't need to overcome the high osmotic pressure. So we're directly extracting lithium from the brine using a lithium intercalation material.
So if I can I ask
Please go ahead. Yeah, jump on in.
So if I understand it correctly, I mean, effectively you're sort of using like a cathode material, or a material which is similar to a cathode in a lithium-ion battery. What effect do you see when you've got a relatively impure natural chloride solution, with a bunch of calcium, potassium, sodium, et cetera, what poisoning do you see of the electrode material by the other sort of competing ions which are present at much higher concentrations? Have you got any thoughts on that?
Yes, definitely. So other ions may be present. So we have a pre-treatment using electrocoagulation. So we hope to remove some of the iron, for example, and other impurities. Also, we plan to include a monovalent selective ion exchange membrane. So if we can go back to one of the slides, well, I can directly say that. So we include a monovalent selective ion exchange membrane, so we can exclude these divalent like calcium, magnesium, and other ions, so that these ions they don't poison our lithium intercalation material.
Okay, so you think there'll basically be like a lithium, sodium, potassium chloride solution would be the ideal feed into that selective electrode there. Okay.
Yes, exactly. Yes.
Okay. All right.
Thank you.
Thanks.
Great, thank you. All right, we're just about at time. So we'll go ahead and move on to our next presentation. Thank you so much. Oh, all right. So it looks like before we move on, we'll go ahead and take a 15-minute break. So if everybody could be back at 4:05 p.m. Eastern, that would be great. See you in a few minutes. All right, we ready to get started again, everybody? Tech D-Cell from Texas Tech University. Are you back from break and ready to get started?
Yes, I'm here.
Great. All right, whenever you're ready, please.
Yeah, I'm ready. Thank you. Okay, good afternoon. This is Madi Mamadi, captain of Tech D-Cell. Along with my team, I'm going to present you an idea of a membrane and also absorption technology for direct lithium extraction. Next, please. So the idea is that our technology is consisted of two different steps. The first step is, we call it intensified membrane distillation crystallization, which is essentially we want to dewater the brine a little bit. And as somebody pointed out yesterday, per 6 molecules of water, there is at least 1 molecule of iron. So if we can try to dewater the brine a little bit, we can bring some of those kind of salts to the supersaturation and then try to knock them out. The second part is the membrane absorber composite, which is essentially we want to provide a modular framework for absorbers to selectively remove lithium. So the progress that we have made to date in phase 1, I will describe it in slide 5 in more details, but we have identified a well brine here in Texas that it has a very similar kind of composition, and it's also unstable. So we want to use it, we want to heat it up and properly handle it and spike it up with lithium if the geothermal brine is not available to us. We also demonstrated the MDC, we evaluated the nanofiltration, and we worked on a TEA and LCA, which I will present those to you. For the phase 3, essentially we want to develop these membrane absorbers, MAX, and integrate it with the MDC that we have currently in place. I will show you some of the results for the MDC, and essentially demonstrate its performance for lithium extraction in the future. We also have very unique thermodynamic model. It's activity-based, high accuracy model that we can essentially predict all the phase diagrams for the brine at any point. And it will be associated with a very comprehensive energy and mass balance model in Aspen HYSYS, which essentially give us a realistic view on this process. And finally, we will use this to draw the TEA and LCA. So this is probably the most important aspect of this slide, so I would like to draw your attention. So essentially what's happening here is that, let me find the, I cannot find the laser, but essentially the brine is coming out of the well. This is very similar to Hudson Ranch geothermal plant. It's based on a 15 megawatts electricity generation. So steam is going through a couple of flashes and crystallizers. We will get some steam, high, low, and medium pressure steam. It goes through scrubbers, demisters, and then a binary steam generator to produce electricity. Then it goes through a primary and secondary clarifier to knock out some of the silica. And as you know, some of this silica is used as sealing crystals in the standard high pressure crystallizer. So what we will use is essentially the outlet from this process, which is the geothermal plant, which is around 130 degrees C. So what we would do with this is we put it into a series of reactions and clarifiers. In the first reactor, we will add lime and air to essentially knock out all the iron and silica. Essentially, we will reduce their concentrations to less than 5 ppm and then remove them in the clarifiers. After this, we believe the temperature of the brine is around 90 or 100 degrees C. Then we will send it to a heat integration process to make sure the heat is properly preserved. And then it goes to a vacuum membrane distillation module. This module is something that we have demonstrated. We can make it almost commercially available. It's being tested in a pilot plant for oil and gas produced water business. So essentially the driving force with this type of membrane process is not pressure. So we are not having those difficulties with all the pressure-driven membranes. There's no osmotic pressure limitation. Here, as long as the brine is at high temperature, the water vapor will diffuse through the membrane and we will collect it on the permeate side. And the water collected here goes to a mechanical vapor compression, which brings the heat, the vapor to superheat. So the brine is getting out of the membrane module. We can design it at any size, and everything is almost commercially available. Then it goes to a heat integration unit to take the heat out of the superheated vapor and bring it back to the brine again. So this way we will protect and preserve the heat inside this concentration loop. So this goes back and forth until we get to a concentration that we think it's ready for crystallization. And everything is going to be modeled and guided by thermodynamic models which we have in place. So then when we get to the certain point, we will send it to this heat integration to the crystallizer. And some of the crystals, some of the salts which will crystallize in the crystallizer, and the slurry of those abundant minerals are going to be mixed with water and sent back to a geothermal to the well. So the product of this is at lower salinity, and it's being sent to the membrane absorber for selective removal of the lithium. Essentially, this is how we are going to deal with all those precipitations and silica, iron, some of the transition metals that are essentially making any other, most of the technologies almost unfeasible because of their scaling and precipitation. Next, please. So in the next step, what we do is we have a 3-stage absorber. The first two are membrane absorbers. Essentially, we are providing very, very porous structure of the membranes with accessible absorbers, and the brine is getting in, and we have kind of at this point, based on the reports available, we have selected a selectivity of 1/100. Most of the reports are providing up to 400. We wanted to be targeting some of the low numbers. So it's 1/100. In the second stage, we are getting almost lithium 1-to-1 with other divalent and monovalent ions. In this stage, again, it's being concentrated. Here we'll get, again, a ratio 1/100. And finally, it gets to a fixed bed of the absorbers. And the product of this is going to be more than 99.9% of lithium carbonate. The reason we chose lithium carbonate because of the zinc prices, and we think that iron-based batteries are now having better market, cheaper prices, so there will be more demand for this. Next, please. So this is the progress that we have made till date. So I was working on the membrane distillation crystallization. Essentially, you can see the design of this experimental parts that we have. We are testing 2 different types of crystallizers, a fixed CSTR crystallizer, and something new that we have been starting working on it is a fluidized crystallizer, which we put the seeds inside and it's fluidized. And then also, what is important is that we started testing with gypsum, which is one of the very difficult materials to crystallize and take out, and we could very effectively remove gypsum up to concentrations as low as 5 ppm. So Shen fabricated NF membranes and tested those, and in reality, I think there's no way those membranes are going to work because the selectivity required for any type of membrane-based processes, it should be more than 100,000 to really make this process working. And if we can really get around the osmotic pressure of about 300 bar. So with Donarin, we did some kind of very basic thermodynamic studies on equilibrium calculations to predict the mineral precipitation. And also Chen published a very accurate model, activity-based model called ANRTL to predict the phase diagrams for lithium chloride. And in the next phase, you want to do experiments with lithium carbonate and lithium hydroxide in order to get this model also working for them and essentially use the model from the beginning to the end to predict the performance. And with Xiao, we did some course T and LCA, which I will tell you a little bit about it. Next, please. So here's another important slide. So this is essentially the non-discounted and discounted cumulative cash flow diagram. So the orange one is for non-discounted and the blue one is for discounted. And essentially, discounted one has a 7% interest rate on the capital. And as you can see, the fixed capital investment for adding this retrofit to any geothermal plant is so low and the revenue is so high that essentially you can throw anything into this separation. So some important numbers here is that this is for 50 megawatts plant, 6,000 gallon per minute of brine with a concentration of 200 ppm of lithium. And the threshold value for lithium carbonate to make profit on this is $13,000 per metric ton. And this process is not sensitive to the electricity price. For these calculations, we buy the electricity with 15 cents per kilowatt hour. So essentially, half of that electricity generated in the plant is going to be used in this process at the cost of 15 cents per kilowatt hour. And essentially, depending on the rates of recovery, if we take 25% of the lithium out, the net present value for a 20-year plant is going to be 1 billion. And if you can remove 100% of the lithium, it's going to be 5 billion. So it's a very, very profitable business. Next, please. Yeah, so to summarize what we have here is essentially we have a very high TRL project that is we think that we can really deal with the high salinity. Of course, we don't have any dependence on water. This process is working independent of water. It requires electricity, which can, green electricity produced in the geothermal plant can be used here. And this process is using the low-grade heat from geothermal brine that it has no other use. So it's another value-added benefits. And we can really find the way to get around silica, iron, and zinc, manganese, lead, based on the thermodynamic model and process simulations that we have. So everything is going to be validated by thermodynamics and process simulations, energy and mass balance. And the other thing is we are a team of dedicated researchers that we hope that we can get around this technology. And with that, I would be happy to answer any questions.
Great, thank you so much. All right, we'll open it up for questions and feedback from our IAP members. And maybe while we're waiting on some IAP feedback, how about I ask a question? Can you talk a little bit about how your solution will improve the environmental impacts of direct lithium extraction?
Yeah, that's a very good question. Actually, we have two backup slides that we did the LCA with Black & Veatch. They're expert in this area. We did TEA, LCA, very comprehensive one based on the database that we have. And something interesting that we found is that this technology has very, very, very limited impact. Essentially, the only impact is the electricity. The most important impact is the electricity that we take out of that geothermal plant. And the rest is just associated with the chemicals that we are using. So we have the data. We are going to provide that in the application for the phase 3, but it's so insignificant that we want to again run it again and make sure that it's exactly what we want to do. But as you look at the process flow diagram, the only thing is being there is the use of chemicals, which is something very conventional in current processing of the geothermal brine at the moment.
Thank you. I'll go ahead and ask another question. In your design, you seem to be very comfortable with looking at water treatment and purification processes, but could you also describe how you've incorporated a diverse perspective in your technology?
You mean having different technologies here?
Yeah, how did you seek out a diverse perspective as you were putting together your technology, as you're learning how to transfer that technology over to geothermal?
Yeah, another good question. So we have been working on this IMDC, intensified membrane distillation and crystallization, for a current project under Department of Energy for treating high salinity produced water from oil and gas business that it has salinities around 150 to 200,000 ppm. And it's in the last 4 years, we have been trying to de-risk this process for such applications, which has kind of very similar to the geothermal brine. And for this one, essentially, we are updating our thermodynamic model. So the first part of the project is essentially very similar to what we are doing there, with some different type of pretreatments to make sure that the geothermal is clear before it gets to the IMDC part. The other part is essentially, after discussing, we have a very broad team. Yue Xiaoshen is an expert in making materials that are selective for very high selectivity membranes and the kind of module. So he just suggested this idea that, oh, we can do this first step to get rid of the osmotic pressure and then reduce the salinity and get the lithium out. And also, Andy is expert in the LCA at Black & Veatch, and Chao Qian and Donor, and also expert in the thermodynamic part of it. So it's a kind of group team. We discussed it, came up with this idea, but the core of this technology is already validated and tested in the pilot scale.
Great, thank you so much for answering that question. All right, is this part of your presentation?
Yeah, this is essentially the
Okay.
framework we use for TA, and the next one is for LCA. So,
Gotcha. Okay. Thank you. Well, we're just about at time, so we will go ahead and move on to our next presentation. Thank you very much. All right, next up we have Team University of Utah from University of Utah. So please, whenever you're ready.
So good afternoon. Can everyone hear me?
Yep.
So I'm Mike McKibben from UC Riverside. Our tri-university team has developed and partially tested an engineered lithium-ion sieve technology for direct lithium extraction from hot brines with a subsequent lithium hydroxide production. We utilize delithified titanium trioxide as the absorbent. Our team is composed of chemical, metallurgical, and environmental engineers, plus a geothermal geochemist. Next slide. Our approach tackles unsolved challenges related to enhanced lithium recovery and high purity lithium hydroxide conversion. Technologies already exist for removing silica from geothermal brines. For example, mesoscale fluidic separators have already been developed and tested with geothermal brines and patented by PNNL for silica separation. The current operators at the Salton Sea field also use patented post-flash reactor clarifier technology to reduce silica and iron precipitation in brines prior to attempting lithium recovery. So minimizing further brine cooling during lithium extraction is critical. Please back up the slide. No, thank you. Our technology addresses the challenge of developing stable materials for lithium separation at plant temperatures and inherent recycling of reagents and water for efficient lithium recovery. Our titanium-based nanoparticle absorbent, which is coated on a diatomaceous earth substrate, has wider absorption performance compared to aluminum-based materials and broader pH and thermal stability compared to manganese-based materials. For the Salton Sea brines, we may refine the substrate and the platform for slightly larger sized absorbent particles. Some other substrate candidates include alumina, alginate beads, or magnetic substrates, which can be separated from the liquids under magnetic fields. Compared with traditional lithium solar mining technologies, our process conserves water, works over a wide range of lithium concentrations, is highly selective for lithium over other competing ions, and regenerates acid reagents used for electrodialysis. The titanium absorbent is made from inexpensive slag that is commonly found at steel arc furnaces. Our proposed process has low power consumption, a low carbon footprint, and can also produce hydrogen gas byproduct for the market. Next slide, please. So here's a schematic showing the lithium absorption step on the left, the lithium elution step in the middle, and the electrodialysis step to produce lithium hydroxide from lithium chloride on the right. So far, we have tested our lithium extraction process with the hydrogen titanium trioxide absorbent using Great Salt Lake brines with 20 ppm of lithium in them. We've tested absorbent stability up to 80 degrees centigrade. In the next phase, we will test it on Salton Sea geothermal brines. Please back up. In the next phase, we will test it on Salton Sea geothermal brines with an order of magnitude higher lithium concentration at more realistic power plant temperatures of 95 to 105 degrees centigrade. It is important to note that the endothermic nature of the absorption ion exchange reaction should promote greater selectivity and capture efficiency at higher temperature and lithium concentrations. So we expect higher recovery under more realistic Salton Sea geothermal brine conditions. Hydrochloric acid is used to elute the lithium from the absorbent. The subsequent electrodialysis step produces lithium hydroxide and releases chlorine, oxygen, and hydrogen. The chlorine is then used to regenerate hydrochloric acid for the elution. Next slide, please. So our project goals are to recover lithium hydroxide with battery grade purity, reduce reagent and water consumption, and lower costs compared with traditional lithium production. For phase 2, we proposed to develop novel ion sieve titanium materials and evaluate their performance efficiency. Milestones achieved from this phase include synthesizing the titanium ion sieve materials, achieving higher selectivity for lithium and nearly 80% lithium capture from Great Salt Lake brines, demonstrating higher pH and thermal stability, reducing reagent consumption, please back up, and demonstrating lithium hydroxide conversion using electrodialysis. Key risks that we addressed include the stability of the ion sieve materials, the high selectivity over other adsorbents, the ease of regeneration, and the feasibility of electrochemical lithium hydroxide production. Next slide, please. So here are some results of our adsorption-desorption experiments on the Great Salt Lake brines. These are at room temperature, showing the brine composition before absorption, brine composition after adsorption, and the element composition. Note the separation factors or alphas showing how selective the absorbent is for lithium versus competing mono and trivalent cations. Solid to liquid ratios for the experiments were 1 gram absorbent per 200 to 400 milliliters of brine with 24-hour contact times at room temperature. Lithium chloride electrodialysis was conducted for 6 hours. Please back up. 6 hours at 10 volts with a final lithium hydroxide product obtained after evaporation and crystallization. Next slide, please. Data on adsorption capacity and desorption elution efficiency are shown on the left, with first order and second order kinetic models fitted to them. Both solid state and hydrothermal methods of synthesis of the hydrogen titanium trioxide absorbent have been tested. The middle chart shows that 70 to 80% recovery of lithium was obtained using the Great Salt Lake brines. The absorbent was reused for 4 cycles. As noted earlier, we expect this endothermic recovery efficiency to improve at higher temperatures and higher lithium concentrations using saltancy geothermal brines. Please back up. Thermogravimetric analysis of the lithium hydroxide electrodialysis product on the right shows a purity of over 90%. Next slide. Shown here is our techno-economic analysis for absorbent synthesis in blue, adsorption elution in orange, and electrodialysis in gray. Units used, prices, and cost per ton of lithium hydroxide are shown. Please back up. Note that the lithium carbonate used to make the absorbent template, which is required for any ion sieve method, is fully recovered and reused. So its initial cost is shown, but not included in the analysis. The only use of fresh water is to make the initial dilute hydrochloric acid for elution. This water is recycled along with the hydrochloric acid. So for phase 3, we will demonstrate that our technology will work effectively with saltancy brines and use results from those studies for more realistic and accurate techno-economic assessments. Geothermal power plants generate waste heat and typically have a 10 to 20% parasitic power load. So the anticipated costs for heating and energy for our process may be reduced if we can harness such internal sources of heat and energy. Next slide. So our next steps for phase 3 will target improvements in the efficiency of our process as follows. We want to improve lithium recovery to greater than 90% at high temperature and lithium concentrations, in part by minimizing proton accumulation from the adsorption ion exchange reaction. We want to concentrate the eluent in lithium chloride, please back up, by recycling it before it is sent to electrolysis for lithium hydroxide recovery. And we want to test the absorbent stability for more than 4 adsorption-desorption cycles, possibly by using iron dopants. We expect to demonstrate improved separation from competing ions, faster kinetics of adsorption, desorption, and more accurate regeneration capacity by using actual saltancy brines at relevant power plant temperatures. This will allow us to develop an integrated working prototype that can be tested in a real plant setting. Next slide, please. So the next steps and assessments needed to scale up our process in collaboration with an industry partner are shown here. Using real brines, refining reactor schemes to improve lithium recovery, and exploring potential heat and energy use from the power plant will be critical. This will allow a final, more accurate techno-economic analysis to be conducted for a full field scale process. Final slide, please. So we'd like to thank the GTO, the prize committee, the industry panel, our industry advisor, Daryl Gallup, and our 3 institutions for supporting our participation in this challenging competition. Thank you.
Thank you, Mike, so much.
And I just want to apologize for the advancement of the slides. It's a ghost, I think, advancing the slides. I'm going to stop sharing my screen for a second, restart the PowerPoint while we do the Q&A.
Apologies from Mike for that.
That's fine.
It was always right when you were about ready to move on.
I guess I stayed in within 10 minutes anyway. Yeah.
Yes, you did. Thank you so much. All right. Well, Lindsay's bringing up those slides that we can share while we're going through some Q&A. Does anybody, the IAP, want to start with some questions and feedback for the University of Utah?
Alexander, it's Jonathan Weisco. Can you hear me?
I can. There's a lot of feedback on your side.
Okay.
Or maybe it's nope, you're good.
Okay.
Go ahead. Go ahead, Jonathan.
Mike, you talk about water savings, and I forget the percentage, 25 or whatever. But my question is, what was your baseline? Where did you start? How did you figure out a number of water use from which to reduce your use?
Yeah, so we're comparing it to traditional solar mining, which is, as you know, wastes a tremendous amount of water. That's our baseline.
Got it. A second quick question. You spoke briefly about harnessing the waste heat from geothermal plants. That may go a little bit. I mean, is that anything you've looked at in more detail as you look at your next phase here, or is that a different kind of a project altogether?
Yeah, that would have to be an additional kind of project. I just know from experience around those plants and talking to the operators, you know, that there is a lot of waste heat generated. Those plants were all built back. Most of them were built back in the 1970s and 80s, and could maybe benefit from some heat capturing technology that's could be applied.
Yep, no question about it. Thank you.
Hey, it's Andy Robinson here. Can you hear me? I'm not sure. I'm on a very sketchy line here. Hi, Mike. Quick question for you. Well, a couple of questions. First of all, what base are you using to buffer the pH when you're doing the loading with of the various brines onto the sort of lithium titanate or metatitanic acid form?
So I'm going to ask our postdoc Raja, who's actually doing that stuff.
Right.
He can unmute himself and talk about
it. Hi, I'll be able to answer that question. We've been currently using ammoniacal buffer, like a mixture of ammonium hydroxide and ammonium chloride for our test solutions. But when we were working with the great salt lake water, we actually used the natural brine without adding any buffering reagents.
Okay, thanks. Second question then, why are you sort of putting the lithium titanate onto kind of a base material? Sort of what's the rationale for that?
So the thing is, most of the titanate material that we are making, they are actually nanoparticles, and the problem with nanoparticles is like it's kind of difficult to separate if we just use the nanoparticles. So if we coat it on a substrate, then we can easily separate them from the liquids.
Okay, thanks. And then final question: why sort of electrodialysis versus, you know, a sort of a more more conventional, sort of 2-cell chloralkali setup for electrochemical conversion? What was the basis for that decision?
The reason why we chose, I'm sorry, let me actually see if we have other members. Let's see.
Jump in for that, Raja, if that's fine.
Oh yeah, I'm sorry. I was just looking for Hasnain, who's another postdoc member.
Yeah,
sorry. Yeah, he'll probably answer.
Question. So the rationale is with electrodialysis, the target is to develop battery-grade lithium hydroxide monohydrate. So we can have high selectivity also with the membranes that we're using, and then eventually the product will be high purity and won't need further processing. So that's the rationale.
So you can deal with more impure solutions coming in to the electrodialytic cell. Is that what you mean?
Yeah, we already have very high selectivity with our titanate sieves, but still there is, as you notice, if there is other cations still there, we can get rid of them and then have further selectivity in the dialysis step.
All right.
Great.
Since we're over time, thanks, Andy, for those questions. And thank you, everybody, for your questions today. We'll go ahead and move on to our final presentation for our pitch event, our innovation pitch event. Last but not least, is Freeman Lab from the University of Texas at Austin. Please, whenever you're ready.
Thank you for that kind introduction. Can we advance the slide, please? We're very pleased and grateful to be here today to share with you our idea for making lithium hydroxide as part of the saltancy brine. I've worked in membranes my entire career in gas separation as well as water purification. I lead one of the Department of Energy's Energy Frontier Research Center, MWET, that is focused on membranes for water purification. We're teamed up with a local startup in the Austin, Texas area called EnergyX, and EnergyX brings a wealth of experience that's valuable for this project. Amit Padwardhan has a long career at Rio Tinto before coming to EnergyX and has been involved in commercializing and scaling up lithium technology. Jamie Vincent comes from a key supplier of electrodialysis membranes and has been involved in a lot of cost analysis and also other operations of electrodialysis systems. And George Go is our membrane expert, and he has a long history of working in this space. Next slide, please. And so the approach we have is to use bipolar electrodialysis to produce lithium hydroxide directly. Next slide. And we'll advance one more, please. And one more. And so bipolar electrodialysis, as it's practiced conventionally, has 3 types of membranes in it. It has a bipolar membrane that has a positive side and a negative side. And this takes water and makes H+ and OH-. So this is where we get the hydroxide for lithium hydroxide. It has anion and cation exchange membranes to help separate the other ions based upon charge. Next slide. And so as we feed brine into a traditional bipolar electrodialysis setup, next slide, we make hydroxide at the bipolar membrane. Lithium moves in contact with that to make the lithium hydroxide. The problem is the magnesium and calcium also move with it. And so if you're going to use this process, you have to have ultra clean, ultra softened brine, which is very expensive. Next slide. And the reason for this is that the cation exchange membranes that are conventionally used are non-selective. Next slide. Our innovation in this space, next slide, is to develop a selective cation exchange membrane. Next slide. And with the selective cation exchange membrane, the magnesium and calcium are rejected and never get into contact with the hydroxide solution. Next slide. And so now when we take lithium across that selective cation exchange membrane. We make lithium hydroxide, we leave the magnesium and calcium behind. If they get into that lithium hydroxide stream, they will foul the membranes. They'll plate out as mineral scale. And so we avoid that with the selective cation exchange membranes. Next slide. And so as a result of this, we can work with significantly less pure brine feeds to this process. Next slide. Next slide. So just to put this in context, this slide shows on the far left-hand side the traditional lithium carbonate to lithium hydroxide process. So you would come with an initial brine, and after some cleanup, such as ion exchange, it would go through a concentration step to make lithium carbonate, and then the lithium carbonate would be converted to lithium hydroxide. The conventional bipolar electrodialysis process takes that same ion exchange and somewhat cleaned up brine and puts it through rigorous concentration and extensive purification to remove those divalent ions that cause the scaling and fouling that shut down the membranes before going to bipolar electrodialysis to make the lithium hydroxide directly. Next slide. The UT Austin Energy X selected bipolar electrodialysis membranes takes that brine and first concentrates it in the Energy X Litus process that is currently being scaled at in pilot tests in Bolivia, and combines it with our selected bipolar electrodialysis to make pure lithium hydroxide. Next slide. So this is a little bit of information that's coming from the lab. Just by way of background, most manufacturers will not sell you a system for bipolar electrodialysis if there's more than 10 ppm hardness in the stream, and some even knock that down to 1 ppm. Next slide. And so we pick up in a model brine system, brine that has passed through an initial ion exchange process. You can see the composition here. Next slide. We have spiked it with additional magnesium to understand better the behavior of these divalents. This is a stream that's coming out of our Litus system, and so it's been concentrated, as you can see, 7x in lithium, and there's also some separation going on here as well. And again, we've spiked the magnesium in this one. Next slide. Now coming out of the bipolar electrodialysis cell, we have virtually all of the lithium that we put into the process, and you can see that we really brought down the magnesium and calcium levels. Next slide. The acid product that comes out still has a bit of the lithium hydroxide in it, but again, essentially no hardness. Next slide. And so we, in just a few hours in a lab scale test, we can recover 27% lithium. If we let that run a bit longer, we get up to 50 or 60% after 6 hours. And we have a test that's ongoing today where the lithium hydroxide is has been increasing from 1 to 4%. And even with 1400 ppm of calcium and 40 ppm of magnesium, we have undetectable levels of calcium and magnesium in the base product. The membranes we're testing are, even at lab scale, are at significant scale. We're testing about a third of a square meter at a time, and tests were started today that double that. So we're testing upwards of half a square meter, 6 tenths of a square meter of membrane. This is a picture of our base product. It is crystal clear, no evidence of particles. There's a little bit of turbidity that may have come from CO2 in the atmosphere getting in the sample as we collected it and analyzed it. This shows our selective cation exchange membrane and our bipolar membrane. The lithium hydroxide solution flows between these two membranes. If there were scaling, we would see it on these membranes, and we see no evidence of that. Next slide. And so far, we've seen that we can tolerate in the range of 1,000 to 1,500 ppm hardness, which we think is a game changer for the use of bipolar electrodialysis in this process. Next slide. So the comparative cost analysis was done by Jamie Vincent. Jamie costed the largest bipolar electrodialysis system currently active in the US at the K. Bailey Hutchison desal plant in El Paso, Texas. Next slide. And he's computed the CapEx and OpEx for Energy X's Litus process plus bipolar electrodialysis. Next slide. and also compared it to a more conventional bipolar electrodialysis that requires extensive purification. Next slide. And you can see that the cost differential is really significant and is well below the cost of spot price for lithium hydroxide now. Next slide. Next slide. And so we're continuing to do work in the laboratory. And this is a lot of that work is aimed at optimizing the membrane chemistry to increase the lithium selectivity, and also to optimize the test parameters, flow rates, voltage, current, et cetera, so that we get the conditions just right for the pilot test. What we need in support for phase 3 is access to brine, representative brine from the Salton Sea that we can put into this system. Next slide. And we're prepared then to, with facilities that we already have in hand at EnergyX, we have bipolar pilot scale bipolar electrodialysis systems at their facilities. We've already containerized that along with their Lidus separation system. One of those containers is now in Bolivia, working on direct lithium extraction, and we'd love to have a chance to use this at the Salton Sea. Basically, the separation processes that we're putting into place here can fit in with any technology that's been proposed for the Salton Sea and help us get to the sustainable and economic generation of lithium hydroxide. We're really grateful to our industrial advisors, Jonathan Weisgall, who's on the call with us today, and his colleague, Mike McNamara. We've had a very nice initial meeting, and we have a couple of follow-up meetings scheduled next week with them. We look forward to their further engagement with us. Thank you so much for your time today and for that excellent slide handling.
Thank you so much. And yes, thank you, Lindsay, for all your slide handling. Yes, on Tuesday and today. We'll go ahead and open it up for questions and feedback. Maybe while we're waiting for some questions, make sure I'm not missing anything in the chat box. We'll go ahead and.
Still here.
Okay, go ahead, Jonathan.
Oh,
yeah.
now you can't hear me.
Yep, I can hear you.
As a non-scientist, please explain to me why it's only the magnesium and the calcium that causes this problem with the bipolar electrodialysis, as opposed to the other impurities.
Yes. So Jamie, would you
yeah,
like
no
to
problem.
address that?
Yeah. So what happens at the surface of that bipolar membrane? It's where OH minus, the caustic, is being generated. So it's coming off the surface. So at the surface of that membrane, the pH is very, very high, and in the presence of magnesium, calcium, and certain other metals, it forms a scaling directly on the surface, so that it's just related to the production of the caustic at the surface.
Got it.
Yeah. Essentially, Jonathan, magnesium hydroxide and calcium hydroxide have very low solubility in the solutions that are of interest here. So they played out on the membrane and in the system.
Alex, let me jump in with another completely non-scientific question, but I'm curious about how you're going. Did you come across any surprises as you went through this process? Well, leave that as just an open-ended question.
Yeah, so I'll ask. Amit Padwardhan was very much involved, along with Angela Kirschhorn, in the initial studies, and I'll ask you guys what your view is of that.
I think the surprise really here was a very positive surprise. We were not expecting that we could achieve feeds containing 1,500 parts per million of calcium to be successfully run in this. We were aiming for lower, but 1,500 is what we are running today, and it's running great. Benny's grad students did some experiments, And they have kind of shown that we could actually push this limit a lot higher. So far the surprise has been a very positive surprise.
Thank you.
We did get a question in the chat box I'll share. How do you see the impact of geothermal brine temperature of approximately 100 C on the performance of BPM or other ion exchange membranes?
So our approach is to pick the brine up after it has been through some initial cleaning and has been brought down to room temperature or thereabouts. Amit, do you want to add anything to that about the assumptions that go into the modeling of the process?
Yes, you're correct, Benny. We pick it up after the pre-exchange step. We are working on the Elliott of that stream, which is at a lower temperature. And what makes that attractive to us is most of the projects and activity in the Salton Sea area is based on some advanced TRL level technologies surrounding the ion exchange piece. So this is really a plug-in or add-on to any of those processes that are being investigated. So we are not trying to reinvent the wheel. We know ion exchange works well. That is what is being tried. This is a way to improve the economics and the product quality, as well as have some positive environmental benefits of doing this.
All right, well, thank you very much. We'll go ahead and end it there since we're just about at time. Again, I want to thank everybody so much for your presentations. These were really fantastic presentations. And thank you again to our IAP members for joining and asking your questions and providing some fantastic feedback for our teams. And then just as a friendly reminder for everybody, your phase 2 submission deadline is still April 29th at 5 p.m. Eastern. So if you have any questions or concerns or anything that's come up, please submit your questions to the GeoLithium extraction at NREL email box, and we will get back to you with that. So if there's no other questions or comments for today, I just want to thank everyone again sincerely. This was a really great event, and I'm so glad that you were all able to attend. And with that, I will say goodbye, and I will talk to you all soon.
Right. Thank
Bye.
you so much. Bye-bye.
Thank you.